Hello, and welcome to the talk on efficient algorithms for public-private social networks, created by the Stanford Scholar Initiative. Why are social networks the poster child for research? It's because of privacy features. Privacy is a major factor in the algorithmic analysis of social networks with different privacy aspects such as public and private friends, private groups, and private circles, such as Google+. In any social media platform, there are many cases where users have hid their friends list, which makes it difficult for the recommendation algorithms to run efficiently. Also, huge network sizes are a bottleneck for efficiency. But why is dealing with social networks important? Because we need efficient algorithms, providing recommendations and making the social circle better, and lead to development of new features. And why is the problem of developing efficient algorithms for social networks hard to solve? Because privacy settings for users must be maintained. Social media data is mostly encrypted. Moreover, most of it is inaccessible due to privacy issues. And massive networks lead to computation overhead. Jim and Mill are facing some problems, so let's see what's going on. Hey Mill, what are the primary research questions that this paper is trying to solve?
I found one. How to model social networks as graphs while respecting the user privacy.
Also, how to answer a particular user query efficiently? You know speed matters.
Yeah, true that. Also, what are the advantages of public-private models against the traditional graph models?
So, let's see what they've contributed. This paper has provided a very concrete contribution by analyzing social usage from a real-world perspective. It introduced the Public-Private Framework. This model/framework helps in computation of different graph properties from each user/node point of view, and thus reduces the computation for the whole graph. Let us introduce the public-private graph models for social networks. In this model, we have a public graph G containing a node U. For each node U, a private graph exists G of U. Think like a private circle in Google+, whose nodes and edges are visible only to the node U and are not public. We assume that each node in the private graph is at most distance 2 away from U. We can safely say that E intersection E subscript U is empty. That is, the user/node's view of the graph is a union of the public and their private graph. Let's find out how the author used this model in answering a user query. So the authors used a two-step approach. They first ran the pre-computation on the public graph G and stored the results. Furthermore, they used the above results in conjunction with the private graph G of U to answer the user's U query. So the methodology used by the authors is as follows. First, they map the social network as a public-private graph. Second, they study the different graph patterns using two algorithmic paradigms known as sampling and sketching. They then determine the privacy features. And finally, they get effective results. Now, let's see how this paper was evaluated. This paper uses two classes of social networking algorithms, namely sketching and sampling. The sketching algorithm includes the size of the reachability tree and centrality measures. The sampling algorithm includes all pair shortest path, pairwise node similarity, and correlation clustering. All of this data are publicly available as part of Stanford's SNAP dataset. The datasets used in the experiment are shown on the right. The efficiency of the author's approach is illustrated by the ratio of A and B, where A is the running time for the author's new algorithm for the public-private model, and B is the running time of the related naive algorithms. In addition, they studied the two different privacy settings, such as the star case and the click case. They also studied the effect of epsilon on what is known as efficiency gains. The smaller the epsilon, the higher accuracy it will have. In this slide, the authors are illustrating the efficiency gains for a size reachability tree and the efficiency gains for a correlation clustering. It is noted in the graphs that the shortest path greatly outperforms the naive solution known as Dijkstra's algorithm. In addition, the algorithm for correlation clustering does not work in a click case environment. Finally, let's see some real-world applications. First, the framework handles the privacy and size issues of the network and generates effective results that can be further utilized to provide better privacy features. It also provides better recommendations and features. Now, we can obtain efficient algorithms for the problems such as heaviest subgraph or community detection. Let's look at some future possibilities of this study. The possibilities from this area of study is the opportunity to get efficient algorithms for even the hardest problems of the social network problem, like community detections, computing other pairwise similarity scores, and most importantly, in recommendation systems. The possibilities are endless. Hopefully you can think of some after reading the paper in detail. That's all for today. Thank you for your time. If you want to listen to more talks like these, please visit scholar.stanford.edu.